Welcome to you. We're continuing to differentiate, and with this video what I'm going to do is teach you how to differentiate some what are called composite functions using the chain rule. Now the chain rule, as you see and as I just said, is going to be used in order to differentiate composite functions, and hopefully you remember what composite functions are. If not, I'll talk about that in the process of teaching you how to use the chain rule. So let me give you a formal definition of the chain rule. The chain rule occurs if you have a function f of x that's equal to u of v of x. Now, when I was referring to a composite function earlier, this is an example of a composite function. A composite function being where you take one function and you make it the input for a second function. And so with a composite function, you're always going to have what I'll refer to as an inner function, which in this case would be v of x. And then you have an outer function, which would be the function u of x. And then we're going to learn how to take the derivative of that. Now, for example, this could be your composite function that you might be asked to find the derivative of. Let's say that f of x is equal to 8 times x cubed minus 4x to the negative fourth power. What are the two functions that we'd be referring to, the inner function and the outer function, or the u and the v of x? Well, the inner function is just what you see in the parentheses right here. In this case, x cubed minus 4x. And so according to the rule that I have, I could call that v of x. We could say v of x is equal to x cubed minus 4x. And then the outer function would be 8x to the negative fourth power. And so we would say that our u of x is equal to 8x to the negative fourth power. So how do you differentiate such a thing? Well, this looks complicated, but according to the chain rule, then the derivative of x is equal to u prime of v of x times v prime of x. All right, now I'm going to break this down, and then I'll show you with the function that I've already made up right here how that actually works in practice. Remember, u is the outer function. That's what I was labeling it as up here. And so first, when you are taking the derivative of a composite function, you take the derivative of the outer function, and notice it has the inner function inside of it. So we say that you take the derivative of the outer function with respect to the inner function. And then what you do is you multiply that by the derivative of the inner function. So you see v prime of x right here, that's the derivative of the inner function. So if you're going to try to remember a way to use the chain rule, what you could say the chain rule tells you to do is this. It tells you that you take the derivative of the outer function and you multiply it by the derivative of the inner function. Now I say doubter dinner sometimes. All right, not quite as good as low d high minus high d low over low low like I taught you with the quotient rule, but nevertheless, derivative of the outer function times the derivative of the inner function, that's how you use the chain rule. Now here, let me show you that put to use. Let's find f prime of x for the function that I gave to you earlier. Now, remember we said that the outer function was essentially 8x to the negative fourth power. And if you're going to differentiate that, you're simply going to use the power rule. You're going to multiply negative 4 times 8, and you'll decrease this by 1. The only difference is that we're going to leave the inner function inside of it. All right, so you're still going to multiply the exponent by the coefficient. So that'll give me negative 32. But in the parentheses, you'll leave exactly what was there. 8x cubed minus 4x, and then we'll decrease by negative 5. Now that's the derivative of the outer function. Then we're going to multiply that by the derivative of the inner function, or in other words, we're going to find v prime of x. Now v of x, or the inner function, was x cubed minus 4x. Its derivative would be 3x squared minus 4, so that's what we'll go ahead and put right here, is 3x squared minus 4. So we did the derivative of the outer function with respect to the inner function, just meaning that you keep the inner function inside the parentheses in this case. And then we multiplied that by the derivative of the inner function, which was 3x squared minus 4. And if there's any simplifying that can be done, generally you do it. In this case, we're not necessarily going to simplify, but we will make this look a little bit neater because I've got this negative exponent there, and so I'm going to rewrite the expression without a negative exponent. Now, The negative 32 has a positive exponent, so does 3x squared minus 4. They would stay in the numerator. You have negative 32 times 3x squared minus 4. And then that would be over the part that had a negative exponent there. X cubed minus 4x. And then we'll change the exponent of that, of course, to the positive fifth power. Now, there's no canceling that can happen here. There's really no advantage to distributing the negative 32, so I would suggest just leaving the answer like that. All right, chain rule tells you to differentiate a composite function, to find the derivative of the outer function, and multiply it by the derivative of the inner function. Let's see another couple of examples. We're going to find the derivative next of the function f of x equals the square root of x to the fifth plus 6x cubed. Now, part of the trick with this is recognizing what's the inner function and what's the outer function. Let's first start with the outer function. You're going to notice the square root symbol right there. Our outer function, or u of x, would be the square root of x, which for differentiation purposes we could write as x to the 1/2 power. And then the inner function is what you see inside of, obviously, the square root function, x to the fifth plus 6x cubed. And so that would be our v of x according to the chain rule. So we would say that v of x is equal to x to the fifth power plus 6x cubed. All right, let's use that to find f prime of x. And we'll start with finding the derivative of the outer function. So think of the derivative of x to the 1/2 power. You, I think, note that would be 1/2 times x to the negative 1/2 power. So for us, we would say it's 1/2 times, but not just an x, because we're going to do the derivative of the outer function with respect to the inner function. So we're going to keep x to the fifth power plus 6x cubed inside of our outer function. And then we'll decrease the exponent by 1, and we'll get negative 1/2 power. All right, that's the derivative of the outer. Now let's multiply that by the derivative of our inner function, v of x, x to the fifth plus 6x cubed, and of course its derivative would be 5x to the fourth plus 18x squared. Okay, so we've taken care of business there, other than just making this look as neat as possible. So let's rewrite the function so that it is in its simplest form and, well, looks as concise as it can be, as it wouldn't technically be in simplest form. Now, just like with the last one, I've got this 1/2 that has a positive exponent. This binomial has a negative exponent. This one has a positive exponent of positive 1. So we'll leave everything with a positive exponent in the numerator, except that, well, let's just leave the 1 there from here. So we'll have 5x to the fourth power plus 18x squared over, and then we can put the 2 from that fraction in the denominator, and then we can put this entire factor in the denominator, x to the fifth plus 6x to the third, and then with the 1/2, and we can make that look still simpler. We can rewrite it with a radical. So 5x to the fourth power plus 18x squared over 2 times the square root of x to the fifth power plus 6x cubed, and that would be it then. So this looks super complicated, and you would have thought maybe it looked complicated to find the derivative there, but I think if you follow the rule, our derivative of the outer function times the derivative of the inner function, it really wasn't all that bad, was it? I hope not. Now, let's do one more example. And this example gets a little bit more complicated because it turns out that sometimes whenever you use the chain rule, you have to use it in conjunction with either the product or the quotient rule, and that's going to be the case here. Now, first of all, what's our outer function and our inner function? Now, I'm not going to write them down separately, but hopefully you can identify them. The outer function would simply be the natural log of x. And then the inner function, our v of x, would be x squared e to the x power. And you're going to notice that that inner function here is a product, isn't it? All right, let's proceed with that in mind. All right, now you'll remember that the derivative of the natural log of x is 1 over x. So we could say it's 1 over x squared e to the x power in this case, because that's the derivative of our outer function with respect to the inner function. All right? And then we'll multiply that by the derivative of our inner function. But as I pointed out a little bit ago, our inner function is a product. And so we're going to apply the product rule, which you might remember as 1d2 plus 2d1. Or in other words, you do the first function times the derivative of the second function. So that would be x squared times e to the x, because e to the x is its own derivative, plus the second function times the derivative of the first function. So second function being e to the x, the derivative of the first function being 2x, like so. So there's the derivative of our outer function. I mean the inner function, if that's not what I said. And now to make that look a little bit neater. Now there's not a lot I could do with the 1 over x squared e to the x power at this point. Let me leave it that way. But if you look within where we use the product tool right here, you're going to notice each factor has e to the x as a factor, and in fact it has an x and an e to the x as a factor. And so I'm going to bring that to the front. Let's bring an x, e to the x power out, and that will leave me with an x to the first power here, and it'll leave me with just a 2 here, like so. Then we can do a little bit of canceling, because we have an e to the x as a factor of this denominator and a factor of the numerator, so cancel that out. And then we can do a little canceling with the x squared down here and the x right there. Of course, that'll completely cancel out the x, and that'll just make that an x. So here's what we've ended up with. Across the numerators, I've got 1 times x plus 2, so just x plus 2, over, and in the denominators I've got x, well, really times just 1, so that would be x. Great. I think that made sense for you. Now, you've learned how to use the chain rule to find the derivative of a composite function by taking the derivative of the outer function with respect to the inner function and then multiplying it by the inner function. Good luck with this. Some of these problems do get really hairy looking, don't they? But you can handle it. See you later.